Okay, so in this video, I'm going to do some collision calculations and introduce some concepts about center of mass and convertible kinetic energy and some things like that, if you're in block 4, you have now probably seen this because you've had 2 extra days of class. And if you're in block 2, then I think several of these things will be new and will be helpful to you in finishing the chapter 6 homework and moving us on into chapter 7. So one thing that is perhaps a secret that some of you didn't know is that I have a spreadsheet that I use to help me in some of the calculations. So you can see in these yellow boxes here, these are the ones that are user editable. There are no calculations that feed into those yellow ones, but there are calculations that feed out from them. So I can set the mass of object A, I can set the mass of object B, and I can set the 2 velocities, and I can set the E for the collision. And there's more in this spreadsheet that I'm not showing you yet. But since every single time when we do one of the collisions, what I suggest that you do is you make sure you get the before table right, so you know exactly what the situation is before the collision. This spreadsheet first does that. So you can see that it calculates the momentum of object A by taking the mass from cell B3 and the velocity from cell B4. It does this calculation right here and then calculates the momentum of 16. And then it does the same thing for object B. It takes the mass from cell C3 and the velocity from cell C4, multiplies them and gets the momentum, and it gets the sign right there. And then for the whole system, I've got the momentum that it adds up. 16 plus -6 is 10, and it sums up those values. And then the kinetic energy, you can see it takes the mass times the velocity again, divides by 2, and it gets the kinetic energy. Same thing for object B, adds the 2 together. And then the relative speed, it takes the difference between those 2 velocities, B4 minus C4, and then takes the absolute value of them. So it doesn't particularly matter which one goes first. Okay, so this gives us the before table. So the new thing that I want to add in addition to this spreadsheet, and you should start working on building your own spreadsheet so that you can use this in future. I want to add in some information about where those 2 objects are before the collision. So I'm going to go over to the whiteboard, and I'm going to say that object A is going to start here at position 0, and object B is going to start way over here at position 20. So this one's at 0 meters I hat, this one's at 20 meters I hat. So that's how far apart they are. And since this one has a velocity initially of 8 meters per second I hat, and this one's got a velocity of -2 meters per second I hat, you can see that this one's going to move in towards the right, this one's going to move in towards the left, and they're going to meet somewhere in the middle. And since this one's going a lot faster, it's clearly going to meet past the midpoint. Okay, so we've got positions, and we know that they're going to move in the next few seconds, and they're going to collide at some point in the future. I also want you to now figure out what is the location of the center of mass of this system. So this has shown up in some of the homework already, so maybe you know how to do this. If you don't, the formula to calculate the center of mass is, let me give myself some more room here. So this is the position vector of the center of mass. For 2 objects, you add up the mass times the location of position 1 plus the mass of the other one times the position of object 2, and then you divide by the total mass. What this is conceptually is a weighted average of the 2 positions. So if I put some numbers in there, we're going to get a mass of 2 kilograms and a mass of 3 kilograms and a position of 0 and a position of 20. And then those 2 masses on the bottom add up. You get 2 plus 3 is 5. So 2 times 0, 3 times 20. So that adds up to 0 plus 60 over 5, which equals 12 meters I hat. So that's the location of the center of mass. I'm going to mark that. This is 5, 10, 12. That's where the center of mass is. So what does that mean? What is the center of mass? The center of mass is kind of it's an imaginary point. There isn't anything actually at that location. But you can imagine if I put a ruler or a teeter-totter underneath the two objects, the place where I would need to put the pivot point so that it would balance is right there at the center of mass. So if it was allowed to teeter-totter around that, because this mass is a little bit lighter and farther away, and this one's a little bit heavier and a little bit closer, those average out not in the center, but a little bit to the right of the center. So that's the location of the center of mass. Okay, before you go on, I want you to predict in your head, in 1 second from now, where's object A going to be? Where's object B going to be? And where's the center of mass going to be? So predict that in your head. Okay, so let's calculate what is going to happen to the position of the two objects and the center of mass. So object A is going to move in by 8 meters in that next second. So it's going to go 1, 2, 3, 4, 5, 6, 7, 8 to right there. And then object B is going to move in by 2, 1, 2. And then what do you think? Is the center of mass going to move? Is it going to stay at that place, or is it going to move? It kind of feels like it's going to move to the right some. So let's see what happens. So this calculation, now we've got 2 times not 0, but 8. So I got to change that to be an 8 right there. And object B is no longer at position 20, it's at 18. And then when I add those up, I get 16 plus 54. That's 70. 70 divided by 5 isn't 12, it's 14. So that means the center of mass moves 2 by about 2 meters to the right. So let me label this. Hopefully it won't get too busy. A1, B1, and CM1. Actually, I'll put that in red. Okay, so I want to make a little table to keep track of the positions of all these things so that I don't forget. We can also look at this representation here of the objects moving around and keep track of them. So I've also got, let's see, over here, another spreadsheet where at time 0, object A was at position 0, and object B was at position 20, and the center of mass was at 12 meters I hat. And then 1 second later, object A is at 8, and B is at 18, and the center of mass is at 14. Okay, so what do you think is going to be the location of the center of mass in 1 more second? Is it going to move again? So let's go back to the whiteboard and calculate that. So 1 second later again, A is going to move 8 more meters to the right. So that's from the 8 to the 16. 9, 10, 11, 12, 13, 14, 15, 16. So there's A at time 2. And then B is going to move 2 more meters into the right. So it's going to be right there too. So we've got A2 and B2. And then, well, since both objects are in that same location right there, presumably the center of mass is going to be there too. So it's going to have moved as well. Let's check to make sure that works out right. So we put in, instead of 8 and 18, object A is at 16, and object B is at 16. That's 32 and 48. 32 plus 48. 32 and 48 is 80. 80 divided by 5 is 16. So that all checks out. So this is the collision. Let me put that in a different color again. The collision is going to happen right there. And at that moment, at time 2 seconds, the object A, object B, and the center of mass will all be in the same place. So let me go back over the spreadsheet and record that. At time 2, it's going to be 16, and 16, and 16. Okay. Oops. So far, it seems like the center of mass has moved. In 1 second, it moved 2 meters, and the next second, it moved 2 meters again. So what do you think is going to happen after the collision? Is it going to start moving backwards? Is it going to go backward the way where it came? You should think about that. Try to make a prediction before we move on. So to do this, we need to actually start doing the calculation. And one thing we're going to do is we're going to pretend that this collision happens basically instantaneously, so that 1 second later is really 1 second after the collision. So the collision happens like really quick. So let's go back over here. How do we set this up so we can figure out what's going to happen after the collision? Well, I think we need to do our standard collision calculations with an E of 0.5. So I'm going to set up a second whiteboard since this one doesn't have enough space to do that calculation. So I'll just put this to the side for the moment and move this one over here. And then, so what do we know going in the after table? We know that the momentum afterwards is going to be m1 v1 plus m2 v2 has to equal 10 because that's what it equaled before. So that's 2v1 plus 3v2 equals 10. And we also know that the relative speed is going to become 5 because the relative speed was 10. The E is 0.5. So that means that v1 minus v2 is going to equal 5. And as usual, we have two possible solutions there. We've got the one where v1 minus v2 is positive, and the one where v1 minus v2 is negative. Okay, well, at this point in the course, we've done this enough times that I can let you in on a way of figuring out which of the two branches is the one we want without having to solve both of them. Let me put in the original velocities. We know that the relative speed started out being 10. That means v1 minus v2 equals 10 because we had 8 minus negative 2 is 10. Yeah? So that shows that v1 minus v2 was positive to begin with. v1 minus v2 was positive to begin with. Okay. If the objects actually hit each other, like physical objects that collide, then the sign of that relative velocity always changes. So when we look at these two possible solutions, this one has v1 minus v2 equal to positive 5. It's still positive. We want it to be negative because that's the one that changes. So this is the solution we want because it's a different sign than it started out off, and that implies that they actually collided. All right. So those are my two equations. I've got this one from the momentum, this one from the relative speed. So then I rearrange that to get v1 equals v2 minus 5, and then 2 times v2 minus 5 plus 3v2 equals 10. And then that's going to give me 5v2 minus 10 equals 10. That means 5v2 equals 20. That means v2 is 4. Okay, and then V1 is V2 minus 5, so 4 minus 5 is negative 1. V1 equals negative 1. There we go. That is the solution I want. V2 equals 4, V1 equals negative 1. So let me go back to the spreadsheet, and I'll show you that that is what I've got over here in my solution for the after. I've got same masses, V1 is negative 1, V2 is 4, momentum of object A is negative 2, momentum of B is 12, that still adds up to 10 as it has to. The kinetic energy is now 1 and 24, that is a total kinetic energy of 25 and a relative speed of 5. And then how much did the kinetic energy change? Let's see, it started out at 70 and it ended at 25. So that's a drop of negative 45 joules. Okay, so now we have new velocities for object A and object B, negative 1 and positive 4. So then let's go back over to the whiteboard and our picture of the collision right here. So what happens after that collision? Object A turns around and goes negative 1 meter per second. Object B turns around and goes plus 4. So after the collision, let's see, erase this and I'll put the return path down a little bit so we can see it. So object A is going to go backwards by 1, right there. And object B is going to go forward by 4 from there. 1, 2, 3, 4. Okay, where is the center of mass? So we've got object A is now at position 15. Object B is now at position 20. That adds up to 30 plus 60. So 30 plus 60 is 90. 90 divided by 5 is 18. Let's put that in the table showing where the objects are. Over here. So object 3 moved backwards by 1 to 15. Object B moved forward by 4 to 20. And the center of mass is now at 18. How about that? Is that what you thought was going to happen? I noticed that the center of mass started at 12, went to 14, went to 16, went to 18. It seems to be going at a constant speed, and that speed seems to be 2 meters per second. So let's keep going. 1 second after that, object A is still going negative 1, so it's now at 14. And object B goes forward by 4 to 24. And the center of mass is going to do what? 14, 24. Let's go back over to the whiteboard. Change this to 14 and 24. And I get 28 plus 72. That's 100. 100 divided by 5 is 20. Perfect. It's gone forward by 2 again. So go back over here and make that go forward by 2. So 13, 28, and 22. That's enough. So what is the center of mass doing? Center of mass is going in a straight line at a constant speed. And it's continuing to do that after the collision and before. Let me go back to this whiteboard. So we saw the center of mass started at 12, went to 14, went to 16, then to 18, then to 20, and then to 22. It just keeps going to the right. Even as object A ends up going back to the left, object B ends up going back to the right. Because B is going faster, that's going to pull that center of mass over to the right. Okay, important conclusion from all of this. Write this out. You should remember it and put it in your notes. the velocity of the center of mass, which is abbreviated cm, is a constant. It doesn't change during the collision or after the collision. And that actually does not depend on whether or not on what the E is. The velocity of the center of mass was 2 before the collision, it's 2 during the collision, it's 2 after the collision, regardless of what happens during the collision. So in the next video, I will follow up and we'll talk some more about why it is the velocity of the center of mass is a constant, and then we'll use that to greatly simplify the way that we solve for what's going to happen in collisions.